In this section, we're going to talk about the matrix inverse. And there are a couple things you need to know about the inverse, and that is we only take the inverse of what are known as square matrices. And that is that the number of rows and the number of columns are the same. So we're only dealing with n by n matrices. And second, not all square matrices have inverses. The matrix inverse works just like the multiplicative inverse. That is, that if I multiply any matrix by its inverse, I get the identity. So if we were talking about multiplication, it would be the number times its inverse gives you 1. And you see that A inverse times A is also equal to the identity. So in general, we said that matrix multiplication is not commutative, but in the case of the inverse, we know that A times A inverse is the same thing as A inverse times A. So it does have a commutative property for inverses only. So just to recap what we've already said, inverses can only be found for square matrices, that is a matrix whose rows and columns are equal. Not all square matrices have inverses, and a matrix and its product with its inverse is commutative. Now lastly, those matrices that do not have inverses are called singular. So if it has no inverse, then it is a singular matrix. If it has an inverse, so any matrix that is invertible, is called non-singular. Here is a formal definition of a matrix inverse. It says that an n by n matrix, again it's square, matrix that is invertible if there exists an n by n matrix B such that A times B equals B times A, which is equal to the identity. So B is therefore the inverse of A, and A is the inverse of B. So to show that something is an inverse of a matrix, it is not enough to show that A times B is equal to the identity. We must also show that B times A is also the identity. On this slide, we see the formula or a formula for the inverse of a 2 by 2 matrix. So if we have a matrix that is A, B, C, D, its inverse is given by the following. Now notice that part of this, which is 1 over AD minus BC, is a special part. Now, if you look at the bottom, we see that if AD minus BC is non-zero, then A is invertible. And if AD minus BC is equal to 0, then A is not invertible. So you can see that this AD minus BC is in the denominator of the expression. This is a scalar that we multiply by this matrix D minus B minus C times A to get the inverse. This part is called the determinant of A. So the determinant of A is AD minus BC. If it is equal to 0, then the denominator is undefined, which again tells us that the matrix A is not invertible. Now let's use the formula to find the inverse of this 2 by 2 matrix, 1, 2, 3, 5. So the first thing we want to do is to find AD minus BC, which is the determinant of the matrix. So notice it just means that we cross multiply the elements of A and we subtract the 1 and the 5, and then we subtract from it the product of 3 and 2. So the determinant, or AD minus BC, is equal to 1 times 5 minus 3 times 2, which gives us 5 minus 6, which in the end gives us a value of negative 1. So the determinant of A is equal to negative 1, which tells us that A is invertible. And we know that A is invertible because the determinant of A is non-zero. Right? So it says if AD minus BC is non-zero, then A is invertible. So we also now would call this a non-singular matrix. And it is non-singular because it contains an inverse. So we have that the determinant of A, which is AD minus BC, is negative 1. So we can now find the inverse as 1 over the determinant, which we see here, times the matrix, where we exchange D and A. So we exchange the 5 and the 1, and the B and C become negative. So this becomes -2, -3. And now we simply want to take the product of the scalar that we have here with the matrix to find the inverse. So the matrix inverse is, of course, 1 over -1 is simply -1. So we have -5, 2, 3, -1. So the matrix that we have here, this A inverse, is the inverse of the matrix A, which is 1, 2, 3, 5. If we wanted to verify that the A inverse that we found, which is 5, 2, 3, -1, is actually the inverse of the matrix A, then we need to show two things, and that is that A times A inverse is equal to the identity, which if you do the algebra here, you'll find is true. And likewise, if we multiply by the inverse on the left of A, we also get the identity. Again, it is not enough just to show that A times A inverse is I. We must also show that A inverse times A is I to ensure that A inverse is the inverse of A. It turns out that we can use this idea of a matrix inverse to find the solution for a linear system. So let's consider the matrix equation AX equal to B. And what I'm going to do now is multiply both sides of AX equal to B on the left by the inverse of A. So I have A inverse times A times X is equal to A inverse times B. Again, this is assuming that A has an inverse. If it doesn't have an inverse, then we would not be able to follow this procedure. So now I'm going to group A inverse with A, and we know that A inverse times A is the identity. So if A inverse is the inverse of A, then when I take their product, I get the identity. We also know from our previous knowledge of what the identity does, whenever we multiply the identity by a vector x, we simply get x back. So now we have that x is equal to A inverse times B. So therefore, A inverse times B is the solution for the linear system AX equal to B. So to find x, all we need to do is find the inverse and multiply it by the constant vector B. Now let's use the matrix inverse to solve this linear system, which is given here. And so you see we've translated the linear system into a matrix equation. And to find the solution, all we need to do is multiply the inverse of A times B. So we found previously that A inverse was given by the matrix -5, 2, 3, -1. So now let's simply take the product of A inverse, which is -5, 2, 3, -1, with the constant vector B, which is 4, 7. That is on the right-hand side of the matrix equation. -6 and 5, which is the solution to the linear system. So in conclusion, if your coefficient matrix A is invertible, then we can find the solution to the matrix equation AX equal to B by simply finding the inverse of A and multiplying it by B. So our solution for this linear system is x equal to the vector -6, 5.